Today we are going to talk about the quadrupole splitting in mass bar spectra. So this quadrupole spectra in mass bar spectra, so quadrupole splitting we will see only when I is equals to 1 or I is greater than 1 or equals to 1. Only in this case we will see the quadrupole splitting in mass bar spectra. So because of the quadrupole splitting, instead of singlet, we will get a doublet like this in mass bar spectroscopy. So there are 4 conditions in which in some cases we will see quadrupole splitting, in some cases we will not see the quadrupole splitting. When I is equals to 0, okay, and when dipole moment also 0, then here EQ will be 0. That means shape looks geometric. Next, I is equals to off. In that case, nu is greater than 0. Nu means dipole moment. In this case also electric that quadrupole splitting will be 0. Shape looks geometric. So in these 2 cases we will not see a quadrupole splitting. And here we will get a sharp signal like this in mass bar spectroscopy. And another 2 possibilities are when I is greater than 1. In this case, dipole moment is not equals to 0 and EQ is greater than 0. This is one possibility. Another possibility, when I is greater than 1, in this dipole moment is not equals to 0 and EQ means quadrupole splitting is less than 0. So in these both cases, this is along the axis, this is along the axis, this is perpendicular to the axis. Okay, so along the axis we will see quadrupole moment greater than 0, and perpendicular to the axis we will see a quadrupole moment less than 0. In these 2 cases we will see the quadrupole splitting, and instead of a singlet we will get a doublet. Okay, so quadrupole splitting is mainly depends upon the spin value, nuclear spin value. So the nuclear spin value, if it's greater than of or equals to 1 or greater than 1, we will see quadrupole splitting. And this quadrupole splitting this quadrupole splitting, if this is quadrupole splitting here, depends upon the size of shape of the geometry of complex and electric field gradient of complex. So when I is greater than 1, this nuclear quadrupole, this nuclear spin will interact with this electric field gradient. When I equals to greater than 1, this nuclear spin interacts with this electric field gradient, and this leads to a quadrupole splitting. And quadrupole splitting depends upon the geometry and electric field gradient of the complex. And here further 4 possibilities are there. This will take geometry, electric field gradient, and quadrupole splitting. Okay, if geometry is symmetric and electric field gradient also symmetric, in that case we will not see a quadrupole splitting. If geometry is symmetric, electric field gradient is unsymmetric, now this electric field gradient is interacts with the nuclear so when electric field gradient is unsymmetric, this interacts with a nuclear quadrupole moment, and this leads to a quadrupole splitting. Okay, next, when geometry is unsymmetric, electric field gradient is symmetric, then also we will see a quadrupole splitting. If both are unsymmetric, then also we will see quadrupole splitting. Okay, so quadrupole splitting is due to the interaction of electric field gradient with nuclear quadrupole moment. Okay, and further, this quadrupole splitting depends upon the geometry of the complex and electric field gradient of the complex. If both are symmetric, we will not see quadrupole splitting. If any one or both are unsymmetric, we will see quadrupole splitting. Now we'll take few examples. We'll see how we will see the quadrupole splitting in those examples. So first we have Fe Cn6 4 minus. So here we have iron in a +2 oxidation state. +2 means it is a D6 configuration. Okay, so this is D6 and low spin, so all electrons will fill in the T2 orbital. So if electronic configuration is symmetric, then electric field gradient also symmetric. Okay, so here it's a electric field gradient is symmetric, and if you see the shape of this complex, this is a perfect octahedral. So for octahedral and tetrahedral both are symmetric in nature, so shape also symmetric. So if both are symmetric, that means we will find only one line in the mass bar spectra, and now we will see what kind of transition is that. So we know that iron, which is present in the ground state, that is iron 57, the spin of iron 57 is ±1/2, and the iron which is present in excited state, that is iron 57 in excited state, that is having spin ±3/2. So here we will see only one transition, so that transition we can show like this. So where we are not seeing the quadrupole splitting, where we are finding only one transition, that transition is because of the from the ±1/2 to ±3/2. So next we have another example, that Fe Cn5 NH3. Okay, so here iron is +2 in oxidation state, same, this is T2G6 is 0, so this is a symmetric in nature. So electron configuration symmetric, so electric field gradient also symmetric. Okay, now we will go for the shape. So NH3 is here, Cn, Cn, Cn. So this is actually symmetric, but overall this is the distorted octahedral, right? So here is the 4 possibilities, and this complex belongs to this category. So electric field gradient is symmetric, but geometry is not symmetric. In that case, we will see the quadrupole splitting. Okay, so here in this case we will see 2 lines in the mass bar spectra, 2 lines in the mass bar spectra. And now what kind of transitions we can see? So when we have one line, that time we see only ±1/2 to ±3/2. When we have 2 lines, so that time what kind of transitions we see? So here, so number of energy levels will be, it depends upon the that is I+1 energy level. So when we have a spin 1/2, that time we will see only 1 energy level. When we have spin 3/2, that time we will see 2 energy levels. Okay, now so we have iron in the ground state, that is iron 57 having a spin of ±1/2, and we have iron 57 in the excited state, that is having a spin ±3/2. So further this will not split, because this will be only singly degenerate, and now 3/2 will split into 2 energy states. This will be ±1/2, and this will be ±3/2. So this is one transition, and this is second transitions. So in this complex we got two transitions. So those two transitions are, one is from ±1/2 to ±1/2, and another one is ±1/2 to ±3/2. Next we have another example here. Fe CN5 NO 3 minus. So this is same as this one, but there is a difference. So imagine that this is for Fe CN5 NH3, and this will be for Fe CN5 NO. So what is the difference here? So the difference is here in this gap. So in this case we have less gap, whereas here we have a more gap. Just remember, when we have a pi acceptor ligand, in those cases we have more quadrupole splitting. Okay, so the order is NO, then CO, then CN, SO3 minus 2, PPH3, NO2 minus, and NH3. Okay, so this is the order. So where we have NO, in NO we see more quadrupole splitting, means the separation. This indicates the EQ. This is for EQ. If the gap between two peak is more, that means that there we have more quadrupole splitting. Where the gap is very less, there we have less quadrupole splitting. In case of NH3, the gap is less. In case of NO, gap is more. That means in case of NO, we will see more quadrupole splitting compared to NH3. And one last example we have, when we have Fe CN4 Cl2. So it can exist in two forms. Cl, this is trans, this is cis. Okay, so imagine that this is having a EFC 0, the electric field gradient is 0, but the shape is not symmetric. Okay, so now we have a quadrupole splitting here. Because of that we are getting a two peaks. So we know that trans is more symmetric compared to cis. So because of that reason we have a less quadrupole splitting here, and since cis is a more unsymmetric in nature, because of that we have more quadrupole splitting here. So these are all applications for mossbauer spectroscopy. I will make one separate video for applications on mossbauer spectroscopy and isomeric shifts later. So I hope that this is about the quadrupole splitting. I hope it's clear. Thank you.